Hello everyone, today let's take a look at QP78. Sorry I had to make the question a little bit small here because it's a lot of words. But this is a conditional probability question involving Russian roulette where you put a bullet into a 6-chamber gun and then you spin it and then both players point the gun at their own head and pull the trigger and whoever dies first loses basically. So now we have a few situations. In part A, the barrel is spun exactly one time before the game starts, and then after that, players take turns without re-spinning. So would you rather go first or second? This one's pretty simple. Imagine these right here, the chambers of my gun, and I'm going to place a bullet randomly in one of them and then spin it, so it's going to be in a random position. And then imagine this chamber right here is the first one to get fired. So whoever goes first is going to shoot that one, and they're not going to die because the bullet's not in it, and then we'll go to the next person, and then they're not going to die either. Next person, they're not going to die, they're not going to die, and then when it gets over here, they're going to die because that's where the bullet is. So now since these players are alternating turns, the first person to go is going to get shot by this chamber, and this chamber, and the other person will get shot by these 3 chambers. And since the bullet is randomly placed, obviously the first person has a 3 out of 6 chance of the bullet getting placed in one of his chambers, and the other person has a 3 out of 6 chance as well. So it's equal percentage, right? So would you rather go first or second? The answer is it doesn't matter because you have 50-50 odds. Okay, now in part B, the difference is that the barrel is spun before every single trigger pull. So now it's asking us, would you rather go first or second? Okay, so now every single time that someone takes a turn after that, the bullet's going to go into a different random position. So the odds that you die on any given turn immediately are 1/6. So for this question, this is what the state transition diagram would look like, right? If we're player A, then we have a 1/6 chance of dying over here, and we have a 5/6 chance that it just becomes the other person's turn, and similarly, they have a 5/6 chance that they pass it back to being our turn, and a 1/6 chance of dying themselves. And in this case, A wins, and in this case, B wins. So if I'm A and I go first, well then the probability that I win is the probability that I get to this state over here before getting to this state. So if I'm player A and I go first, well then I'm starting in this state right here, and then the probability that I win from that state, which I'll denote as probability of A, is equal to, well, 5/6 times the probability that I win from state B, which I'll call the probability of B. There's just a law of total probability. I have a 5/6 chance of not dying and a 1/6 chance of dying when it is my turn. Obviously, if I die with 1/6 chance, then I have a 0% chance of winning. Now, if it's B's turn, the probability that A wins, which I'm calling the probability of B, I know it's a little bit confusing, but it's just better for notation. But the probability that A wins from this state is equal to 1/6 in the case when B dies, right? He dies with 1/6 probability. And now when it's B's turn, he has a 5/6 chance of not dying, in which case it would go back to being my turn. So 5/6 of the time, it'll be my turn again, and my odds of winning will be exactly the same. So now all we have to do is plug this in right here, and we get that the probability of winning when we start in state A is going to be equal to 5/6 times 1/6 plus 5/6 times the probability of A, and then we can just rearrange and solve for the probability of A. So this times this will be 25 on 36. When I subtract it over to the other side, I'll get 11 on 36 times the probability of A is going to be equal to, well, 5 on 36. And then when I multiply each side by 36, I get the probability of A is equal to 5 on 11, so a little bit less than 50%. Also, one way that you could even solve this faster is by noticing the symmetry in this diagram, right? So how do we apply that symmetry? Well, again, we know that the probability that we win if we're player A and we go first is just going to be equal to 5/6 times the probability that we win from state B. Now we can use symmetry to note that the probability that A wins from this state right here is equal to the probability that B wins from this state over here. And the probability that B wins from this state over here is equal to 1 minus the probability that A wins from this state, right? So the probability that A wins from this state is just going to be equal to 1 minus the probability that A wins from this green state over here. So 5/6 times 1 minus the probability of A. And again, when you solve for this right here, you're going to get 5/11ths again. And just finally, one more way you could have done it is with the infinite geometric series. So again, if we're using the geometric series, we use the law of total probability. We know that the probability that A wins is just equal to the probability that B dies on each of his turns summed up, right? And then this is what it would look like if you started writing the terms out and you notice the pattern here. Basically, this would be the probability that B dies on their first turn. This would be the probability that B dies on their second turn. Why? Because we'd go 5/6 over here, 5/6 chance we go back here, 5/6 chance now it goes down to B for his second turn, and then a 1/6 chance of him dying, and then this would be for his third turn, and etc. And if you wrote out the geometric series, this is what it would look like right here. You'd have this term on the outside, 5 on 36, and then you multiply that by the sum of this infinite geometric series, and you could bring this square inside, so you get 25 on 36 inside here to the power of k. Then we know the infinite geometric series formula. This would just be 5 on 36 times that, which would be 1 on 1 minus our common factor of 25 on 36, which would give us 11 on 36 on the bottom, and then that would give us 36 on 11. The 36 would cancel, and we get 5 on 11 again. So yeah, sorry about that. Went into a lot of different methods, but basically the best one, in my opinion, is just going to be this one right here, where you can actually draw out the Markov chain and visualize what's going on. Well, would you rather go first or go second? Well, we just calculated that your odds of winning when you go first are going to be 5 out of 11, which means your odds of losing are 6 out of 11. So you have a higher chance of losing than you do winning. So obviously you'd rather go second, in which case you'd have a 6 out of 11 chance of winning. So for part A, we were indifferent, and in part B, we want to go second. Okay, so now let's do part C and part D, which should be pretty simple. In part C, instead of 1 bullet, we have 2 bullets randomly placed in the chamber. Your opponent goes first and is alive after the first trigger pull, and you are given the option to spin the barrel. So should you? Well, if you have 6 bullets in your chamber, we placed 2 randomly, so let's just say they went here and here. So these bullets would be in random positions if you did spin the barrel, and then your odds of dying would be 2/6, which is equal to 1/3. Now, if instead your opponent went first and is still alive after the first trigger pull, and you chose not to spin the barrel, well, then there's going to be this chamber right here that we know did not have one of the bullets in it because the first person didn't die. So we're going to have 5 chambers remaining and 2 bullets left. So the odds that you die on the next chamber are just going to be 2 out of 5. So our odds of dying are greater if we don't spin than they are if we do spin. So do we want to spin the barrel? Yes, we want to spin the barrel. Now let's go into part D, which is basically the same setup as part C, except in this case, we know that the bullets are actually right next to each other. So the probability that we die after a spin, well, the bullets are consecutive now, but there's still 2 bullets in 6 chambers. So the odds that this top chamber, the one that we're going to shoot, has the bullet in it are still 2/6, which is equal to 1/3. Okay, now the key difference is that the probability of death when we do not spin it is going to be different than what it was in part C. So let's look at that. So the person who went first didn't die, so now we know that this chamber right here does not have a bullet. But now for our 5 remaining bullets, well, we have basically a block of 2 bullets right here, and then we have 3 non-bullets. Okay, but now since we know that the bullets have to be consecutive, well, that means that we can basically just treat this right here as a block of 2 bullets, and then what's the probability that this block of 2 bullets is in the front? Well, it's just going to be 1/4. That's just because I have 4 items now, 1, 2, 3, 4. By symmetry, anyone being in the front has a 1/4 chance, or I could also just say, okay, I have 4 factorial ways to permute these 4 items, and I have 3 factorial of those permutations where this one is in front. So now my probability of dying if I don't spin is actually lower than my probability of dying if I do spin. So do I want to spin in this case? No, I do not.